Ви бачите слайди?
Yeah. Yes, we can see the slides. So, hi everyone. I hope you're well. Yeah, today we'll have another series of the presentations related to the topic that we may call beyond building blocks and chemistry services. And my name is Yuri Moroz. I'm VP of Sales and Marketing at Enamine. And yeah, today, as I said, we'll have a webinar related to material science, that a second webinar in the series related to the topic that we are probably not familiar at the market. But anyways, we have such products and services, and would be happy to provide them with you and all our customers. So before we start, I would like to mention just a few rules about the webinar. So we have a speaker today, and he will present his slides. Then you can have an option to ask questions, so you can type them in Q&A box, which is below, and if at some point you or your colleagues missed this webinar, you can always see the recording, which will be available soon after the end of the webinar. And as always, please follow us on social networks like LinkedIn and Facebook to find out more about the upcoming event. So yeah, so today it's my really great pleasure to introduce to you our today's speaker, Sergey Kolotilov, professor, doctor of sciences, corresponding a member of the National Academy of Sciences, and deputy director scientific work of Prysarjevsky Institute of Physical Chemistry. Sergey serves also as a senior scientific advisor at Enamine, and basically leads this part of the services and products that are related to material science. So with this, I would like to give a word to Sergey, and yeah, looking forward to exciting talk.
Yuri, thank you very much for your introduction, and thank you for the opportunity to show our work, which we perform in Enamine in collaboration with some academic institutes. So today, I would like to tell about our work in the field of inorganic chemistry, in the field of coordination chemistry.
Sergey, maybe you can click on this, full screen.
I tried to do it, but it doesn't work.
Okay.
Don't know why.
Uh-huh.
I can try to turn off and start again. I don't know why it doesn't work.
Yeah, it's odd.
Same. Maybe I can continue like this.
Yes, yeah. Go ahead. Sorry.
Because it doesn't work.
Yeah.
So I would like to tell about work in the field of inorganic and coordination chemistry, which we do. We do it in Enamine. We have some own facilities, and a lot of studies we do in collaboration with two institutes of the Academy of Sciences. In Enamine, we have laboratory of catalysis, and we have some equipment at home. It's NMR instruments, chromatography, analytical and preparative, IR, and session analyzer. We also have scanning electron microscope and vacuum vapor deposition unit. And in collaboration with Centers of Collective Use of the National Academy of Sciences, we do a lot of studies. I will tell more details in this presentation. There are two centers of collective use. It's a porosity and structure of nanomaterials in Prysarjevsky Institute of Physical Chemistry, and the second one, X-ray single crystal diffractometry in Institute of Organic Chemistry of the National Academy of Science. So what we do here, you can make custom synthesis of inorganic compounds and coordination compounds. development of processes in the field of inorganic and coordination chemistry, solution of different scientific tasks in the field of inorganic and materials chemistry. We can do a lot of work in the field of catalysis, and I will show some selected examples today. And within this task, you can make screening of conditions for use of metal catalysts and selection of the most important, most efficient system. Some examples of work of services which we can do in the field of inorganic synthesis. It's a synthesis of inorganic compounds, especially anhydrous compounds, air-sensitive compounds. We have several glove boxes to work with such compounds, and inorganic compounds which are not available from other suppliers. We can also develop functional materials of specific destination, for example, solvents, porous materials, different porous materials, and chiral materials. And we can develop carriers for catalysts, for example, synthetic zeolites, silica molecular sieves, nanosites, zirconia, etc. I would like to draw attention. We have very good experience in the synthesis of zeolites. Maybe our experience is one of the best on the territory of former Soviet Union. We can make compounds for medicine in the field of inorganic chemistry. It's drug-like compounds, some biologically active complexes, for example, platinum, palladium complexes, and so on, metal complexes with peptides. And we have some experience in creation of nanoparticles for drug delivery. For example, magnetic particles or labeled particles with quantum dots. And of course, we have experience in work with homogeneous catalysts, heterogeneous catalysts, and screening of conditions for catalytic reaction. Some selected examples. So of course, it's not the full list, it's just some representative examples. You can do anhydrous salts, which you can see here, and some of these salts are very sensitive to water, even to traces of water. You can do compounds which are air sensitive, like nickel with cyclooctadiene, or copper-1 salts, or some, I would say, intermediate organic and inorganic compounds like phosphorus chloride, which you can see here. And complexes, specific complexes for medicinal chemistry, for example, compound of ruthenium, which you could see. And we do a lot of other work. For example, we have a full cycle of regeneration of palladium from palladium waste. And we almost don't lose palladium in the company because we have regeneration, our own regeneration. We have experience in synthesis of organometallic compounds and new products which we can propose now. It's organozinc compounds. The compounds which you can see here, they are shelf stable. And we perform special studies of stability of these reagents. And you can claim now, we can say that they are stable for several months and they don't lose their properties. So I would say it's a very interesting outlook for use of organozinc chemistry. Also, we can perform synthesis of different metal complexes of 3D, 4D, 5D, and 4F metals. We can work with all kinds of ligands. And we can do metal complexes for catalysis, like Buchwalker catalysts, complexes with bands, Grubbs catalysts. And we have experience in scale-up and characterization of these compounds. We can make catalysts for asymmetric synthesis, in particular asymmetric hydrogenation, catalysts for photochemistry, and catalysts for electrochemistry. I will show some examples. And of course, we can perform synthesis of known compounds and new complexes, and development of ligands and complexes, especially for customer tasks. Here, there are some examples of Buchwald catalysts, which we do in our in-house projects. The company, Enamine, consumes a lot of such catalysts for synthesis, and we can do it for research. And we do it by our own, in our own laboratory. And we optimized protocols for preparation of up to 100 grams of some of these catalysts in 1 run. And also, we perform synthesis of iridium photocatalysts for in-house use, for our in-house projects for research. Some examples of iridium photocatalysts are shown here. And now we can do such systems up to 25 grams from one synthetic run. And they are used in some reactions. An example of this reaction you can see here on the slide. In the field of materials chemistry, one specific direction is the development of solvents. So we can make characterization of solvents provided by client to evaluate capacity for application in different purposes. For example, water wastewater treatment, and so on. As well as we can develop some new solvents for specific tasks of the customer. And also, as I said, we have very good experience in synthesis of zeolites, synthetic zeolites, and molecular sieves, and we can make synthesis, modification, and adaptation of these systems for different tasks. For example, we can prepare composites of metal particles or metal oxide particles for catalysis or drug delivery. And here are two approaches to prepare such systems. It may be incorporation of magnetic particle into porous matrix. So, for example, like molecular sieve MCM41, or development of metal particles inside porous matrix, inside the pores, for different purposes. It can be magnetic particles, or it can be catalytically active particles, or it can be luminescent quantum dots. And also, we have good experience in the preparation of 2D materials like graphene oxide, and other like molybdenum disulfide. And we study such systems for catalytic and for other applications. We have good experience in optimization of processes. For example, on the slide, you can see the results of optimization of synthesis of fused pyridines from cyclic ketones and propyrogylamine. This reaction is known, so we were not the ones who found this reaction, but this reaction could be performed on gold-containing catalysts. And it was very good, it was stable, but the problem is that gold is expensive. So we tested different copper-containing systems and different conditions, and we found conditions to carry out this reaction in a multi-gram scale, in some dozen of grams scales. And now we can prepare ketones, pyridines from ketones using copper systems. On the slide, you can see ketones which we tested, and ketones which are in red, they did not give good products, but another compounds gave very good yields of pyridines, with the respective pyridines. A new service which we launched this year, it's a selection of catalyst and reaction condition for some special purpose. For example, a guy who performs synthesis gives two reagents A and B, and we try to find a catalyst, base for this reaction, solvent, and good temperature. We can perform screening of different conditions and use different catalysts from the library which we have. It's our own library, and we can find good conditions to perform this reaction. And then, if required, we can make further optimization for scale up of this reaction to up to 1 gram. Also, we can make heterogeneous catalysts for different reactions by deposition of metallic or binary nanoparticles to different carriers from solution, or by formation of metallic or composite particles, for example, metal plus carbon, by pyrolysis of selected precursors on the carrier. And we can make complete characterization of these particles, examination of their size, phase composition, and other properties. And we have all procedures for quality control. It's very important because different batches of such systems can have slightly different properties. So we can our own procedures to control the quality, first of all, reproducibility and conformity to our internal standard. One of the examples, we studied a series of cobalt-containing systems for hydrogenation of heterocyclic compounds. These systems were formed by pyrolysis of cobalt complexes deposited on different carriers. And among the systems which we synthesized, we found the best one for suitable for hydrogenation of heterocycles. And we use them for hydrogenation of quinoline and substituted quinolines in a scale up to 100 grams. It's very interesting in my opinion because these systems are very cheap. They do not contain palladium or other noble metals, but they give quite good results and they can be stored for a long time on air without loss of their properties. And such catalysts are now on stock in Enamine and they are used for hydrogenation in some cases. Another example, it's a selection of the best palladium catalyst for hydrogenation of conjugated DNs. So the formulas of these DNs you can see on the slide. I will not take time to explain why it is important. But the problem was that DNs are not very well hydrogenated because of conjugation. And due to high conjugation energy, they usually require much more harsh conditions for hydrogenation compared to usual alkenes. So we found a series of palladium catalysts deposited in carbon, and we can prepare this reaction in very mild conditions compared to what we had before the beginning of the study. I would like to tell about physical methods for analysis and research which are available for our internal projects and for projects for external consumers. So briefly, in summary, we have a very wide range of equipment for characterization and for research. We have single crystal X-ray diffractometers, I will tell more. We have powder X-ray diffraction, microscopy, transmission and scanning electronic microscopy, dynamic light scattering. We have very good experience in adsorption, and it's a method for characterization of surface porosity, and we can extract a lot of information from these experiments. We can measure surface acidity, and we can evaluate surface of metal or metal particles by chemistry of carbon monoxide. We can carry out almost all kinds of spectral studies. We have very good experience in electrochemistry, and of course, elemental analysis. It's CHMS, X-ray fluorescence, and EDX, and derivatography. For single crystal X-ray determination, we use facilities of the Center of Collective Use X-ray Single Crystal Diffractometry in the Institute of Organic Chemistry of National Academy of Sciences. There are two diffractometers, and they're modern diffractometers, and you can solve X-ray structures of many, many compounds. It's a quite simple experiment now at present. And of course, you can use it for metal complexes for determination of their structure and even for confirmation of their structure conformity to known compound. For transmission electronic microscopy, we use facilities of Center of Collective Use Porosity Structure of Nanomaterials in collaboration of Institute of Physical Chemistry of the National Academy of Sciences. We have a transmission electronic microscope. It's a microscope PEN 125K. And some representative photos which we obtained on this instrument, you can see on the picture, on the slide. We have own scanning electronic microscope in Enamine, and we use it for scanning electronic microscopy as well as for EDX analysis. Here are some representative photos obtained by this microscope. And also, we use the capacity of this microscope for determination of phase composition of compounds. Please pay attention. You can see two figures, and these figures are the same part of the surface. It's exactly the same. But left one is measured in the secondary electron detector. The right one is a backscattered electron detector. And in this mode, you can see light particles, white spots, it's palladium particles. So we can differentiate carrier, light carrier, and heavy palladium by scanning electron microscopy, and we use this option very, very actively. Also, you can perform EDX analysis. We do it in conjugation with SEM for determination of element presence and for evaluation of relative element content. For example, you can see results of analysis of two systems. It's a silver salt of organic acid, which you can see, or platinum deposited on carbon. In the first case, we wanted to be sure that there is only silver and no other metals, as well as to evaluate composition of this compound. So what we found is quite well corresponds to what we expected. For EDX, I will say it's a good result. For better checking we need sation, we can do sation, but EDX we can make much quicker. And by EDX we can check traces of other elements, for example, copper or nickel or other one. In the second one, we wanted to be sure that there is only platinum and no impurities of palladium, for example, or nickel. And we could confirm, we could see that sample contained only platinum. Also, we have access to X-ray fluorescent analyzer. And again, we can check purity and semi-quantitative composition of compounds by X-ray fluorescence. It's much more simple than EDX, but it's less sensitive compared to EDX. Two examples, it's platinum and carbon. We wanted to check purity, and we found that it was not pure. It contained iridium and gold. And another one, it's cesium phosphate. Again, we wanted to check composition, and we found that it contained too much cesium. Probably there was impurity of cesium carbonate. At least it's a tick that we have to purify the compound, and we cannot use it directly as we have it. For powder X-ray diffraction, we use diffractometer Bruker D8 advance in Center of Collective Use in IPC. It's a modern diffractometer, and it works very well. We can make X-ray diffraction for phase analysis, as well as for evaluation of particle size by widening of diffraction peaks. And also, we can perform cell-tertiary electron diffraction using transmission electron microscope. And sometimes it gives very interesting information in addition to powder X-ray diffraction, because we can get diffraction pattern from a small part of the sample, and we can make conclusion about uniformity of sample and the presence of crystalline particles and some other conclusions. New service which we launched in Enamine recently, it's a search of conditions for crystallization compound, because we found, and there were reports in literature, that phase composition could make very serious influence on the properties, especially for medicinal chemistry and for some other applications. So we can find different conditions for crystallization, and you can check phase purity, phase composition, and also you can confirm it by optical microscopy or by scanning electronic microscopy. As I said, we have very good experience in measurement of adsorption. And from adsorption isotherms, we can evaluate, you can extract a lot of information about porosity, about specific surface, about size of pores and energy of interaction of the surface with different probes. You can carry out adsorption of different gases like nitrogen, oxygen, methane, carbon dioxide, and hydrogen. We have two instruments for it. It's symptomatic 1990. And one more instrument I will show later. It's a very interesting method which we can use. It's a chemisorption of carbon monoxide. So this method, in our experience, it's a very powerful tool for determination of particle size and for evaluation of accessible surface. The idea of the method, we study adsorption of carbon monoxide at room temperature, and we got isotherm like this one. Then we reduce pressure to 0, but some carbon monoxide is not dissolved because it's held by the metal on the surface very firmly. Then we measure the second isoterm, red one on the figure, and the difference between them is the quantity of carbon monoxide which was absorbed by metal. So the first one is metal plus carrier. Red one is carrier only because metal is already filled with carbon monoxide. And the blue one is the difference between two isotherms. It's absorption of pure metal. And if we suppose, or if we accept that one molecule of carbon monoxide is held by one atom of metal, we can calculate surface of metal, dispersion of metal, and estimate size of metal nanoparticles. And it's very useful if you cannot see small particles by transmission microscope. There were several publications where it was shown that the results of particles size determination by carbon monoxide sorption very well conform to size of particles determined by electron microscope. And last year, we launched a new instrument for absorption in addition to the previous one, which I showed. It's an instrument which allows to measure absorption of 3 samples simultaneously. And we have this device and a station for probe preparation. So at present, we can measure 4 samples per day, and we can make complete characterization of surface, porosity, size of pores, energy of absorption. And I would say it's very, very good. It gives a lot of information to us. Also, we can perform experiments on gravimetric absorption of some compounds, of volatile organic compounds, I would say, like methanol, benzene, cyclohexane, chloroform, and so on. It's a more complex experiment compared to the previous one, because previous one is done automatically, and this one is done, I would say, by hands. But you can obtain new information about interaction of sorbent with these volatile organic compounds. We have 2 instruments for measurement of IR structure, infrared. I would say it's a quite routine experiment, nothing interesting. But in addition to IR, we can make characterization of acidity of surface by spectral measurement of probes. For example, you can measure absorption of pyridine. Then we measure IR spectrum. Then we perform desorption of this pyridine at certain temperature, for example, 30 Celsius degrees. And again, we measure IR spectrum. Then we perform desorption at higher temperature, for example, 50 Celsius degrees. And again, we measure IR spectrum, and so on. We have special gas cuvette for this, and we can measure 4 samples at the same time, 4 pellets here. And by this analysis, we can evaluate quantity of acidic centers. It depends on the quantity of pyridine, or it's governed by the quantity of pyridine which is absorbed. And we can differentiate breasted and Lewis acidic centers. Because pyridine is absorbed by these centers in a different way, there are different shifts of IR bands, and by intensity of these IR bands, we can calculate, I would say it's evaluation, but it works very well. We can calculate quantity of different sites, acidic sites. And in addition, we can measure not only pyridine, we can measure, for example, D-terbutylpyridine or 3-terbutylpyridine. And difference between absorption of these pyridines can give information about size of pores. Small pyridine goes inside all pores, large terbutylpyridine goes inside only very large pores. Also, we can perform characterization of acidity by thermodesorption of amines, for example, ammonia. And we can again evaluate quantity of sites which absorb ammonia and the relative strengths. So strength of sites, it depends. It's evaluated by the maximum of temperature where desorption occurs. And in addition to this characterization of acidity, we can make automatic titration, and we can calculate quantity of acidic sites which work in solution. We have good experience for this. These studies are very important for development of such or some catalysts, because sometimes acidity of surface is critically important for some reaction. for organic reaction and for laboratory scale and for industrial production, sometimes acidity plays very, very important role. Not only for catalysts, for solvents as well, but for catalysts, it's kind of critical and important. We have access to Raman spectroscopy. We have in the Center of Collective Use in the Institute of Physical Chemistry of the National Academy of Sciences, we have a microscope with a Raman spectrometer. It's a new instrument, and we can perform analysis of Raman spectra from very small pieces of surface. We can compare the surface even in one sample. Two representative examples. Here on the left, you can see Raman spectrum of molybdenum disulfide. So unexpectedly, we found that there were a lot of bands which were not bands of molybdenum disulfide, and it appears that it was oxidized molybdenum sulfide, even molybdenum oxides, and it could explain some effects which we observed. And also we can make characterization of materials which have carbon, like graphene-like materials, by measurement, for example, of ratio of intensities of different bands. We can make conclusions about quantity of defects and so on. For thermal analysis, we have different derivatographs. It's a device which measures change of weight upon heating and heat effect. And for example, we use this instrument to evaluate thermal stability of diazoketones. These are, I would say, new class of reagents. These diazoketones are shelf stable. They're stable at room temperature. They can be stored for a long time. And to evaluate their stability, we use thermogravimetry. We found that the composition temperature was much more than 100 Celsius degrees. So these diazoketones, they can be very promising reagents for organic synthesis. We have experience and we have access to dynamic light scattering. Again, it's a center of collective use in Piotrowski Institute of Physical Chemistry. For example, you can see the results of evaluation of particle size for some particles. It's an organic compound in water. Depending on conditions of preparation, particles of different size formed. This method is very suitable, but I would say it should be used in combination with transmission electron microscopy, and preferably in combination with X-ray diffraction, with evaluation of crystal size by Scherer equation, by widening of reflections. But these three metals together, they go. Sometimes they give very good results. We have very good experience in electrochemistry, and we can do cyclic voltammetry, preparative electrolysis, chronoamperometry, and we have experience in evaluation of electrocatalytic properties. We have several potential states and several sets of electrodes for different tasks, and both stationary electrodes, as you can see here, and rotating electrodes for measurement of kinetic of electrochemical reactions. This is one of the examples. It's our work, evaluation of redox properties of a set of cobalt complexes. And these complexes can act as a catalyst for formation of organosin compound, the equation you can see here. Just to evaluate electrocatalytic properties of these compounds, we measured cyclic voltammetry curves for one of the compounds. It's cobalt complex with xanthos. And upon addition of organic halides, it's a right figure, the current of reduction grew very significantly, and it's a very good sign of electrocatalytic activity of this complex. Also, we developed procedure for preparative electrolysis, and we could find conditions for production of Bohr-protected nickel carbonates in a multi-gram, in hundreds of gram scale. And I would say I think it's a success, because these compounds were not, especially this compound, it was not commercially available, and those ones which were available, they were very expensive. After our work, we can do these compounds. It's much cheaper and much more efficiently compared to the previous methods. Also, we can make studies of electronic spectra, and using this technique, we can make identification of compounds and study of stability in different solvents. For example, on the slide, you see a spectra of a series of cobalt complexes. Left one in THF, tetrahydrofuran, and right one in DMF, dimethylbromamide. So you can see that in DMF, all spectra are almost the same. It's a sign that these compounds are composed. But in THF, they are stable. We can perform monitoring of reaction course, measurement of reaction kinetics, determination of concentrations, and solve some specific tasks like determination of electronic gap widths for semiconductors, like zinc S, zinc O, cadmium S, and so on. And also, as I mentioned, we perform synthesis of photocatalysts for our in-house projects. And we can make complete characterization, full characterization of this photocatalysts. In particular, we can measure the luminescence spectra. Again, for identification, for evaluation of their properties, as well as for materials chemistry, we can evaluate efficiency of applied generation for new inorganic and coordination luminophores. So this is a team of laboratory of catalysts. So it's not all people who work in this direction, but I would say it's like a core of our team. And again, we can perform custom synthesis of different compounds, development of process, and we are ready to solve scientific tasks in the fields of inorganic and materials chemistry, as well as tasks in the field of catalysis, like synthesis of new catalysts and screening of conditions for use of such catalysts for preparation of organic compounds. Thank you for your attention.
Yeah, thank you, Sergey. That's really great presentation. I hope with it, our listeners and hopefully those who will be watching this video will find out more about Enamine, again, beyond building blocks and chemistry services and biology services that we provide. So yeah, if you have any questions to our today's speaker, please type them in a Q&A box. Yeah, we don't have them at the moment, but I have few. So Sergey, you mentioned chiral materials that basically you were doing some sort of sorbents and chiral materials. Have you tried to make the chiral phase for chromatography columns?
Yes, we are working on it, and now we are developing two directions. So first one is modification of cellulose to make it suitable for chiral chromatography. Second one is reproduction of phases like pyridyl phases. It's immobilization of chiral amino acids and their derivatives on silica. We have some results. So now at present, we are not ready to replace commercial phases by our own phases, but we are working in this direction.
Thank you. Also, you mentioned thermal stability analysis. Do you have only access to TGA or some other things that can be used by our customers?
We have our own TGA, I would say, in the Research Institute, which we can use, I would say, any day. And in one other center of collective use of the Academy of Sciences, there is a device for differential scanning colorimetry. But it's not our instrument. So I would say we have access, but I cannot guarantee that we do it immediately. We have to ask. So maybe it will take a week or maybe more.
Okay.
So two methods. It's derivatography, our own, and differential scanning colorimetry.
Thank you. So you also mentioned single crystal X-ray analysis. Can you explain, how do you typically work with such requests?
Oh, It's a very interesting question because I like this method very much. And maybe 10 years ago, I worked in Rennes in France, and by myself, I solved more than 100 structures. So it's very amazing, and it's very intriguing work. At present, there can be two approaches. First one, if somebody has a crystal, and if it is good crystal, he goes to the center collective use and asks operator of the instrument to perform X-ray analysis. Usually it works very well. Maybe today or tomorrow we'll get an X-ray structure. If there is not a good crystal, it's a matter of good luck. So the most important is to prepare a crystal. We have some experience. We have different techniques to grow this crystal. It can be just crystallization or crystallization with very slow crystallization or mutual diffusion, for example, diffusion of some liquid to liquid or vapor to liquid, or diffusion of reagents, one towards another one. So if you have a crystal, I would say it's 90% of success. And later, you just ask a guy to measure it, and you get an X-ray structure one day.
Yeah, thanks. Thanks. Also, you mentioned about this, the kind of the condition scanner where you use different catalysts. So how many catalysts do you have at the moment?
At the moment in our library, we have about 30 catalysts for CC coupling, and I would say about maybe 8 or 9 photocatalysts. It's iridium systems, but we can prepare other catalysts. I would say what I said. It's a catalyst which we use in screening. So if there is a task to perform to find conditions, and if there is some specific idea which catalyst we have to use, we use the catalysts from our library. But I would say every week we synthesize some catalysts, for example, for in-house projects. Maybe some manager asks to make a new catalyst, and we do it. So our capacity is not limited to this stock. We can make more.
Okay. And how fast do you typically do one screen? Is it like within a few days or day?
For screening, I would say maybe one day. If everything is ready. So if you have catalysts, if you have reagents, maybe one day. Sometimes if there is some specific demand for base, for example, and we have to prepare it to make it very dry or to find it, it may take several days. For preparation of new catalysts, it depends on the structure. You see, the water catalyst is very, very wide. So sometimes some simple salt like zinc chloride, it can be used as a catalyst. Should we count it separately? I don't know. But typically, maybe to prepare a new catalyst with complex organic ligand, it may take a week, maybe 2 weeks. Of course, there were some cases where we could not make a catalyst. We failed, but it happens, of course. But typically 1 or 2 weeks for preparation of a new one.
Thanks, Sergey. Yeah, I think there is one question related to growing the crystals. About but you just mentioned, and you responded to there are different ways to crystallize the compound. So probably it's just you don't have much to add.
Once I spent maybe 1 year for growing crystals, and I even had night dreams when I was working on growing crystals. It's my favorite task to grow crystals.
Yeah. What is the largest compound you could crystallize and basically solve the structure?
In our experience, we worked only with coordination compounds. Maybe the largest, it was 12 nuclear manganese complex. Or the largest, how you count? On the quantity of heavy atoms, it was 12 nuclear manganese complex. But we solved a structure of a nanocube, which consisted of 8 trinuclear moieties. But in fact, it had very high symmetry, and we had to solve only 1/8 of it. So, but when we multiplied it by symmetry operations, it appears that it's a very large molecule. But crystallography independent part was not so large.
Yeah.
We have no experience in solving of structures of peptides. It's a special chemistry. We can try, but we have no experience at all, frankly. But for inorganic compounds, maybe 12, 15 heavy atoms, more than 100 atoms in total.
Mhm.
A lot of
Okay.
depends on symmetry. If it's a symmetrical compound, it can appear to be much more easier. The most difficult is to solve a structure of compound of intermediate symmetry, like rhombic group or hexagonal group, because you can spend several days to find a space group. And after you ask somebody, please help me to find a space group, and he says 5 minutes and he finds.
Yeah, I remember doing this the same again 10 years or more ago. Anyways, I don't, okay, let me see. I don't think we have more questions today. So I would like to thank you, Sergey, for this really nice presentation. And again, thank you everyone who joining us today. If you have more questions related to this effort that's just been presented to you, as well as to all our products and services, please do not hesitate to contact me or contact us at inquiry@enamine.net or contact us at LinkedIn. Yeah, with this, I would like to, again, thank you one more time, Sergey. Thank you everyone who joined us today, and I would like to close webinar. Have a good one.